Good morning, everyone from Kingston, Ontario. I'm Arijit Chattopadhyay, working under Dr. Elizabeth Steele from Geological Science Department of Queen's University. So today my topic is morphodynamics of deepwater Moki fan systems from mid-Miocene sections of offshore Taranaki Basin in New Zealand. So before we proceed, let's have a relook on the major factors controlling the dimensions of individual turbidites and submarine lobe geometry. In the last 5 decades of humongous research that has been gone to understanding deepwater turbidites and submarine lobe and fan systems, a huge amount of information is now in our plate to discuss about. Out of that, I'm just highlighting the major factors like confinement, basin slope, local topography, and sediment supply. Those are the major factors. They control the dimensions of individual turbidites and submarine lobe geometry. They also influence the larger scale submarine fan morphology. Dimensions can vary even within the single submarine fan. This is the research that I am carrying on, and I'm going to present the initial part of my research outcome so far, which may be a little basic, but please bear with me. The hypothesis that I'm going to test in this research whether the sediment dispersal patterns have any bearing on the spatial distribution of individual lobes within deepwater fan systems beyond the influence of basin topography, or whether the individual lobes migration is independent of external forcing on the system or not. Coming to the forefront, the mid-Miocene section of Moki Formation of Taranaki Basin. This is mostly, not mostly, this is fully reported from the subcrop of subsurface through deepwater drillings of Taranaki Basin in the offshore section and also on the onshore partly. But mostly the Moki Formation is developed in towards the offshore part of Taranaki Basin and further towards deepwater Taranaki Basin, and it is individually sandwiched in between the Manganui and the Mohakinto Formation of the Mid-Miocene. The spatial distribution of the Moki Formation is mostly driven by the deepwater sediment dispersal. At the same time, if we look at the Miocene time isopack or isochron thickness map, we see there is a structural pattern guiding the sediment thickness present in this part of the Taranaki Basin. This is mostly due to the dextral transpression and oblique subduction between Australian and Pacific plates, resulting the hinterland elevation in the New Zealand area and sediment dispersal throughout Miocene and beyond. I have obtained the data set from New Zealand Petroleum and Minerals of the 2018 data pack. So that has a huge amount of 2D and 3D seismic data as well as the well data sets. So here I am just highlighting the paleogeographic map in the inset corner of the right side, where I am just transferring this outline of the already mapped Moki Formation equivalent deepwater fan systems and the present configuration of the seismic data that is available for more insights. So we can see that the 3D, the outline with the blue, and the vast amount of the 2D data set at the center that has a huge seismic coverage even beyond the limit of the mapped Moki formations fan systems. So that's my primary research objective, that how we can further outline and more in a more detailed way characterize the Moki fan system. For that purpose, I have segregated 130 wells for my consideration out of more than 1100 wells. The vertical wells with complete suite of well logs through Miocene sections of Moki fan systems that I am considering, and I'm focusing at the beginning mostly on the full suite of gamma ray logs. Let's have a look how I proceed with the 3D seismic mapping of the Moki fan complex. It's reported from the literature that the Moki formation is typical. It's typical with its blocky signature and coarsening upward stacking pattern with the gamma ray log signature that we are seeing over here in this well section. If we look at the composite panel from the 3D seismic, we can easily see how the successive stacking of the Moki lobes are stacked vertically through the compensational stacking geometry. At the same time, we can see the down dip progression vis-a-vis the aggregation on the forefront. On the left side of the shear channel, we can see the lateral as well as the downlap terminations of the facies. The more detailed surgical mapping has revealed the younger channel facies that has entrenched the successive lobes with time. If we take an arbitrary section following the depositional and structural dip, we still see the broad signature of the gamma ray logs that is present all along from south to the north as we move around this section following the structural and the depositional dip as well. Now I just want to highlight that through my mapping, how we can describe the compensational stacking of the Moki fan-lobe systems. If we look at the left side, there is a panel section, a composite panel section where I have just highlighted the broad portion of the seismic that I have focused on my mapping. I have tried to map around 7 successive Moki lobe systems, and the corresponding figures are going to appear on your screen as I scroll through. So you can see the bottommost signature of the Moki lobe systems from the seismic 3D seismic RMS map. I'm just moving up now successively. The second one, now we see the channelized morphology. The third one, we see the entrance channelized morphology into the lobe system, progressing towards the northwest. There is a lateral spread of the lobe system. At the same time, the channel has been continuing with their entrenchment. This is a partially detached system as per the preservation goals. The next is a beautiful prograded channel system vis-a-vis a lobe system as well. And this is the topmost lobe system we could map in this 2D in this 3D data set. But is this the end of it? I think this is the beginning of it, and I'll discuss in the next slide as well. Because if we look in this 3D data set over here, it has a potential to move further towards northwest, and we can see clearly from these triangulation of the 2D data set that I'm going to further my interpretation into it. So inferring the further outward aerial extent that we have so far estimated in a broad way, it led to a kind of a area of more than 4,300 square kilometer. So there is a lot more to scrutinize within this area and to highlight how this composite lobe system has been distributed spatially and vertically. So concluding with this short talk, that the distribution and the composite lobe systems is guided by the deepwater sediment dispersal patterns in this part of the world. The composite lobes migrated under the combined influence of internal and external forcing of Taranaki Basin. There is a scope that I am planning to further quantitative estimation of the lobe dimensions from the Taranaki subsurface in combination of outcrop and physical experimental data. Thank you. Any questions?
Thank you very much, Arijit, for this fascinating world of 3D seismics. It's quite astonishing how much you can do and see with 3D seismics.